occurs when the outcome of one event does not affect the occurrence or the outcome of another event. So, for example, and kind of shown in this image here, let's say you have these marbles. You have 2 blue ones and 3 red ones. You select a marble at random, and you put it back in the bunch, and then you pick another marble. The first event does not affect the outcome of the event because you have not changed the total number of marbles in like your hand that you're picking from. So in words, an independent event are 2 events that occur if and only if, ooh, look at that conditional statement, if the probability that both events occur is the product of the probabilities of the event. I want you right now to put like little bubbles around this formula right here. We're going to be using that all day. It says the probability of A and B occurring, so the first event and the second event occurring, is equal to the probability of the first event times the probability of the second event. So we're going to be multiplying fractions today and then eventually turning them into percents. Let's see what this looks like. Now, we've seen this image before. It was on our last notes, but I'm going to ask you different questions about it. It says, a student is taking a quiz, randomly guesses the answers to 4 true-false questions. The sample space below is used to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. Here's some things we need to do to solve this kind of problem. Number 1, we need to decide what event A is, and we need to decide what event B is. Event A is going to be that we guess question 1 correctly. Event B is going to be that we guess question 2 correctly. Then we need to look at our data to see how many times those 2 events occurred. So notice that in our sample space here, they're written in order. How many times does the first letter happen to be C? Okay, here's one time that the first letter is C, so we got question 1 correct. And then we have this chance that question 1 is correct, and here as well, and here as well. And oh, look, this one has question 1 right, and this one has question 1 right. This one has question 1 right, and boom, question 1 is right. How many total times in my sample space did we happen to guess question 1 correctly? 8. Okay. So we're saying that the probability of A occurring happens 8 times out of a total of how many chances here? How many total options did I have in my sample space? 16, I think. Did I count wrong? Honest question. Is it 16 or 18? Okay, cool. So then in our calculators, we go 8 divided by 16, which we may be able to do in our head. We'd get 0.5, and we change that to a percentage, 50%. So 50% of the time, we have guessed question 1 correct. Let's do the same thing for the probability of B occurring. So let's look at our sample space. How many times in my sample space was the second question correct? I see it here because the second letter is C. You look through the rest of the sample space. How many times was the second letter C? Okay, so here's where I see the second letter being C. We saw 1 already. 2, 3, 4, 5, 6, 7, 8 times. Did we find all 8? We're just looking for where the second letter is C. So the probability of guessing the second question correct is, again, 8 out of those 16 attempts in my sample space, which is 0.5 or 50%. Now, we've done all of this to help determine if these events are independent. For it to be independent, we also need to find 2 things. Looking at the table, we need to find the probability that A and B occur at the same time. So can you look through your sample space and find the number of times that both the first letter was C and the second letter was C? For example, I'm looking for one where the first and second letter is C, like this one. How many other times are both the first and second letter correct? Look through your sample space, see if you can find them. How many did you find? 4. We have 1, 2, 3, 4 times that the first and second letter were C. Okay, so that probability is 4 out of my total of 16. That's 0.25 or 25%. Now that's all fine and dandy, but what we need to do is determine if the formula that we've put the purple cloud around also works, and we get the same exact number as here. So using the purple cloud formula, we would check to see if the probability of A and B is equal to the probability of A times the probability of B. We've already found the probability of A and the probability of B. What's the probability of A occurring? 50%. I'm going to go back to using the decimal just because it's easier to we'd have to turn it into a decimal to type it in our calculator. What's the probability of B occurring? Let me color code this for you so this makes more sense. I'm getting this from the blue. 0.5 again. Okay, in our calculators, what is 0.5 times 0.5? .25, which is what percent? Okay, fabulous. Now we check our two equations here. For it to be independent, this number and this number must be the same. Are they the same? Yes, so since they are the same, therefore we know that these two are independent. If those were different numbers, we'd say it's not independent. One of them affects the other. Now in this scenario, that kind of makes sense because answering one question and then the next question doesn't have any effect on each other. You could guess A's all the way down your page and that would be fine. It doesn't affect how you answer questions. This is an independent event. Now that was a whole lot. It's like we did 4 problems in one. So take a second and look through it. Is there a part that does not make sense? Because I can go back over it real fast. Let's do another example of an independent event. So we're not going to prove that this one is independent. I'm telling you right now it's independent, and it makes a lot of sense why. As part of a board game, you need to spin a spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and then a number greater than 3 on your second spin. Okay, here's what I know. Event A is going to be that we get a 5. Event B is going to be the event that we get a number greater than 3. When you're spinning a spinner, does the total number of numbers on your spinner ever change? Like, do you get a 3 and then the 3 goes away at all? No, the spinner never really changes. So these are going to be independent events, which is why we're not proving it's independent. The scenario leads us to believe it's independent. So we need to find the probability that we have A and B. That's our goal. Meaning we need to know the probability of A and the probability of B so that we can multiply them together. Okay, on this spinner, how many opportunities do I have to roll a 5? 1 out of how many total opportunities? 8. There's my probability for A. I'm not doing them as separate problems this time, I'm just doing them together. For B, we want a number that's greater than 3. Not equal to 3, but greater than 3. How many numbers on the spinner are greater than 3? 1, 2, 3, 4, 5. There's 5 opportunities for me to get a number that's greater than 3. So the probability of B is 5 out of those 8 sections. Okay, I wanted to do this way because we sometimes make our lives harder trying to make our lives easier. I do not want you to use fancy fractions when you do this, but I do want you to use parentheses. So I'm going to show you in the calculator once how I want you to type this in, because in this unit, again, don't use the fancy fraction. Yeah, when we press enter, we get 0.078. I'm going to add one more decimal, 1. Can we change that into a percent?
Yes, no, maybe so.
Yeah, what is that as a percent? 7.81%. So we have a 7.81% chance of getting both of these things to happen 2 rolls after each other. Very quickly, when you add constraints to an event, your probability goes down really quick. Again, really you need to make sure you understand probability before you try to go to Vegas. Just saying. Okay, I have a question for you. Just because I didn't do this as 2 separate problems, where did I get the 1/8 from? Who can answer that for me? It's because there's only 1 chance out of 8 chances to roll a 5. And probability of A is the probability of getting a 5. Where did the 5/8 come from? Yeah, there are 5 numbers greater than 3 on this wheel out of 8. So the probability of getting a number greater than 3 is 5 out of 8 total opportunities. So we just multiplied those together, made it a percent. Sound good? Now, proving something is independent means that we have to do the problem like number 1. But for the most part, you're going to be smart enough to determine if something is independent or dependent without having to do the math. So the next 3 examples, we're just going to determine if the situation means that it's independent or dependent events. In part A, Nicole has a bag of candies. She takes 1 candy out of the bag, puts it back, and then takes another piece of candy out of the bag. Are those 2 events independent or dependent? Does one affect the outcome of the other? No, this is actually going to be an independent event, but let's talk about why. There's one really key phrase to let us know that it's independent. I want you right now with your highlighter, your circle, your star, whatever you do to really make something emphasize. I want you to super emphasize the words puts it back. Since Nicole took that candy out of the bag, put it back, we have not changed the total number that is in the bag. Meaning 1, whatever she pulled first, she could put it back and pull whatever she wants out of it the second time with no effect from the first to the second. That's an independent event. This is so important. We're going to go back up to the top of our paper and we're going to add the following word underneath the word independent events. You're going to write the word replacement. Nicole replaced the candy that she took out before she did the next event. If there is replacement, meaning you do not change the total number in your experiment, it is an independent event because we've replaced the thing we took out. So if there is replacement or no change to the total amount that we're being used in our experiment, it's an independent event. Part B says a 6-sided dice is rolled twice. An odd number is rolled each time. Does the first roll affect the second roll when you roll a die? No, because you're just rolling a die. Did the total number of faces on that die change from the first to the second? No, so it's like we put it back. This is also an independent event. But if you read number C, if you read this third option here, it says Kevin has 4 horror books, 3 anime books, 6 romance books on his shelf. He will choose 1 book at random, keep it, and then choose another book. Does him choosing the 2 books constitute an independent or a dependent set of events? Another way to ask this, did Kevin put it back? No, he kept the first book and then chose another random book. So he had changed the total number of books on his shelf from the first event to the second. That is not independent. It's a kind of event we're going to call it a dependent event. Again, because he keeps it. That's huge. So if you change the total number of options from one event to another, that makes it dependent. But if you don't change the total number, it's independent. Okay, when you're ready to go to the back, we're going to start talking about dependent events in more detail. Now, just like Kevin's book example, when we have a dependent event, the occurrence of one effect definitely does affect the occurrence of another. So let's highlight these words. This is dependent event. Whatever happens first totally affects what happens second. So if you look at the example they gave you up here with the picture, it says, we still have our marbles in our hand. We pick one out, and without putting it back, we pick another one. Do you see how the total number of marbles in my hand has changed before I select the second one? That means that it is a dependent event because the first one affects the second one. So our key words for ourselves here is we're going to say without replacement. If you keep one of the items that you selected, or the first event definitely affects the second, that is a dependent set of events. So for example, number 4. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. Explain why this situation is an example of a dependent event. What's the key words to tell you that it's dependent? Set it aside. Okay, circle, highlight, star, underline that part right there. The phrase set it aside means that you did not put that dollar bill back. You kept it. That means that you changed the total number. Ooh, I spelled that word wrong. Let me try that again. Changed total number in the bag. If you change the total number of options you have, it is a dependent set of events. But the formula we use to find if they both happen is still the same. So to find the probability that both events A and B will occur, I'm still going to use that purple equation from the front page, which was the probability of A and B is equal to the probability of A times the probability of B. Okay, let's actually do this one. We didn't even read the events here, but event A is that the first bill is $100. What's the probability that you have 20 $1 bills and 5 $100 bills in a bag and you randomly draw out a $100 bill? In that bag, how many $100 bills are there? 5. Out of how many total bills in the bag? 25, because there are 20 $1 bills and 5 $100 bills. So we have a 5 out of 25 chance of randomly picking out a $100 bill. But event B is again that the second bill is $100. Remember, you kept the first bill. How many $100 bills are left in the bag? 4 out of how many total bills in the bag? Ooh, we kept one though. So is there still 25? No, there's 24. See how the total number changed from 25 to 24? We are doing a dependent set of events. Now at this point, we turn to our calculator, because again, this is not math we're going to do in our head necessarily, and we're not going to use our fancy fractions. We're just going to use parentheses and the regular divide key. Go ahead and tell me what the probability of both events A and B occurring. So we should have gotten that this is 0.033, which if we switch that to a percentage, is 3.3%. Having 25 options is a lot of options, so our chances of randomly drawing that $100 bill twice in a row, pretty low. Pretty low. Okay, so things I need us to notice here. Notice, we did not change the formula we used for independent and dependent events when you're trying to see if two things occur at the same time, essentially. But we wouldn't have them be equal to our sample set like on the first example if we just found the number of occurrences where that happened, if that makes sense. Okay, practice problems number 5 and 6 say, determine whether the events below are independent or dependent and then find the probabilities. Number 5, you are trying to guess a 3-letter password that uses only the letters A, E, I, O, U, and Y. Whew, all the vowels. Letters can be used more than once. Find the probability that you pick the correct password, Y-O-U. Is this independent or dependent? Another way to ask this, did we change the total number of options each time we pick a letter, or did we keep the total number of options the same? The same, because we can use a letter more than once, yeah? Since it says letters can be used more than once, that's an indication that this is an independent event. Because we didn't change the total number of options from choice to choice. So if we wanted to find the probability that we would guess the password Y-O-U from these letters, what's the probability of guessing the Y correct? How many Y options out of those letters are there? 1. Out of how many letters can we guess from? A, E, I, O, U, Y. Out of 6 options. Okay, so we picked a random one. We're hoping that we picked the Y 1 out of 6 times. What's the chances of us picking the O? How many O's are there in my options? 1 out of 6. And then we go to the U. How many opportunities do we have to pick the U? 1 out of 6. If it was a longer password, we'd keep multiplying those events together. This is 3 events all multiplied together. Okay, turn to your calculator. What is 1/6 times 1/6 times 1/6? Remember, don't use the fancy fraction, just use the regular divide key and a bunch of parentheses. Yes, so it's real small, 0.0046. And if we make that tiny number into a percent, it is 0.46%. That's a less than 1% chance of someone guessing your password when the password is 3 letters long and they only have 6 choices. Think about when you make a password. First of all, it usually has to be like more than 12 characters long, and you can use all of the alphabet and all those special characters. So the chances of you getting your password guessed by a human, not by a computer can do stuff faster, but by a human, real low, unless you give them hints. Okay, let's see what happens though if we change the scenario. Let's say when you're making this password, it gives you the same letters, but it says specifically that you cannot use letters more than once. Is that independent or dependent? Dependent because you're changing the number of options each time. This is a dependent set of events. So we're going to find the probability that we pick A-I-E. Okay. The first time I pick a letter, I want it to be A. How many A's do I have in that list of letters? 1 A out of how many letters total? 6. Okay, then we can't use A anymore, so we cross it out because it says we can't repeat it. We want to pick the I. Out of the remaining letters, how many I's are there? 1, but out of how many total? 5, because we got rid of the A. We cross off the I. How many opportunities do I have to pick E? 1 out of 4, because we changed the total number of options for ourselves. Go ahead and do this one in your calculator. 1/6 times 1/5 times 1/4. 0.0083, which changes to 0.83%. Now here's life lesson from today. Which one has a smaller percentage of getting your password guessed? When you repeat letters or when you do not repeat letters? Which number is smaller, 0.46 or 0.83? 0.43. When you repeat letters, meaning you are allowed to repeat letters, you actually have a better chance of your password not being taken. That does not mean make your password 00000, because that's way too easy to guess. I'm saying if you don't change the total number, your probability is much smaller, which means for a password, it's much safer. That's your life lesson for today. Last little tidbit for today, a new type of probability called conditional probability, which leads it exactly from dependent events. Conditional probability is the likelihood of an event or outcome occurring based on the occurrence of a previous event or outcome. So obviously these are dependent. There's a really interesting way we write conditional probability. So instead of just saying probability of A and B, you'd say something like this. That bar in the center is the word given. So you would pronounce this the probability of B given A. Meaning we know A has to occur, and then we decide if B occurs. So the probability of B given A is how you would say that. And we'll stay on conditional probability for the next few classes. This is like a little preview. But in the example for conditional probability, it says the table shows the number of male and female college students who played collegiate basketball and collegiate soccer in the United States in some recent year. Okay, we have another two-way table like we did for our pizzas. How many total collegiate soccer players are there in this table? To find that out, we add these numbers together to find the total number in the column called collegiate soccer. 73,763 total. Whoa, I put an extra 6 for no reason. Total collegiate soccer players. How many total collegiate basketball players are there? 59,865 total collegiate soccer players. Now, the reason we need these totals is because we know from a two-way table you have to use probability with totals. So to keep going, how many total male collegiate players were there? We'd add those numbers straight across. This is 69,103. The total number of female collegiate athletes in this table is 64,525, meaning that the grand total number of collegiate athletes in my table is 133,628. Okay, again, all I'm getting is the numbers if I add up all the columns and the rows from these two-way tables, because I know eventually I'm going to need total number of things happening. All right, let's read the actual question here. Part A says, find the probability that a randomly selected collegiate soccer player is female. Here's how we would write this. We were asking for the probability that someone is female given they play soccer. So we already know they play soccer, so we're only looking at the total number of soccer players because we know we're just looking at those. So of the total number of collegiate soccer players, how many of them are female? If we look at our table, 36,523 of the collegiate soccer players are female out of a total number of 73,763 total soccer players. Notice that in this one, unlike the pizza example from the other day, I didn't use that big grand total in the corner. I just used the total number of soccer players because I know it has already been determined she's a soccer player. Then this is just regular probability. In our calculators, we do 36,523 divided by 737.63. And you know what? I'm going to add a little bit of information here since these are our notes. So you know where these numbers come from. This is our female soccer number over our total soccer number, if you want to write that down for yourself. So you're not like, where these numbers come from? Okay, if we do this math, beep, beep, bop, that's a calculator question. You'd get 0.495, which means that 49.5% of collegiate soccer players are female. Part B is going to be for you. The question says, what is the probability that a randomly selected male is a collegiate basketball player? So I want you to do the problem exactly like we did part A, except you're not looking at female soccer players anymore. You're going to look at male basketball players. Okay, let's chat. Instead of female soccer, what are the two words that you should have in your probability statement? Very good. So probability of male given they play basketball. And I'm going to shorten that to b-ball because I'm lazy. Now in this one, two words should I have on the top? Male basketball. And what word should I have on the bottom? Ooh, basketball. Okay, cool. So now we know where we're looking. In your table, the number of male basketball players is 31,863 out of a total of how many basketball players in general? That's the 59,865 number. Remember, unlike last time with the pizza example, we don't use the total because we're looking specifically only at basketball players. When you do that math in your calculator, you would get 0.532, which is 53.2%. Questions, comments, concerns? Conditional probability we will revisit multiple times. So if this is the part where I lost you today, that's okay. The main thing is noticing the difference between independent and dependent events, like the password example, where you either do replace or don't replace the number of letters you use every time. Now, just like last class, our classwork assignment today, which is homework if you do not finish it, is an experiment of sorts. Okay, I'm going to walk through how to do the experiment, and you're actually going to do this experiment with your table, because I only have 9 versions of the experiment for us to use. So a paper bag contains 3 colored cubes or squares. There's 1 blue, 1 red, 1 green. And first, before you do anything in the experiment, you're going to do the theoretical probability that the result in your table occurs. So I've done the first one for you. The first event is the probability that you get a red first. So like here's red. So that's 1 out of 3 chances because there's 1 red out of 3 blocks in here. Event B is that you either get a blue or a green. So there are 2 blue or greens in here because 1 is blue, 1 is green. That's a total of 2 that are blue or green. So theoretically, I should have this happen 22% of the time. You're going to do the same thing for 2 more events. The event that I get a blue first, and then a green, and then the event that I get the same color twice. So like a red, and then a red, a blue, and then a blue, a green, and then a green. Then you're actually going to run the experiment. This side of the paper, somebody's going to pull out a block. I pulled out a blue one. On this side specifically, it says to, this is the important part, return it to the bag. Does that mean this is all independent or all dependent? Independent, because we put it back. Then you're going to draw out another one. So like I randomly drew out a red one. So I would look at my tally sheet here. Did any of these want me to get a blue first and then a red second? No. I wanted red, then blue or green, blue and then green, or the same color twice. So this one didn't have any tally marks on the table, so I'm just going to put a tally mark to the side. You're going to run this experiment 15 times. You may or may not get a tally for these things, but 15 tally marks off to the side or in this that you actually want, kind of like the spinner or the dice game we played last time. Then you'll find the actual experimental probability from these 2 events happening. I know this is a lot of information, just hang on with me. Flip this paper over.
So I'll keep my money, baby.
On the back, it looks the exact same, yeah? Here's the big difference. What are you doing this time? Keeping it. Does that show an independent or a dependent experiment? Dependent, because I'm changing the total number in the bag. So like I draw the first one, it's red. I draw the second one, it's green. That would have been one of these. Red and then green. So you'll do the same thing on both sides. Calculate the theoretical probability, then actually run the experiment for the experimental probability. Okay? You're doing this as a team, so we have to basically get it done before we leave today. The reflection questions will be yours to do individually, but the numbers and the experiment you do with your table. I know there will be questions, but are there any big questions before we just start? Okay. Send someone from your team to come get the bag and then start working on your theoretical probabilities first. Then you can run your experiment.